Section 13.3 is called Measures of Relative Position. Statisticians often talk about the position of a value relative to other values in a data set. The most common measures of position are percentiles, quartiles, and standard scores, which are also called z-scores. Assume that the values of a data set are rank ordered from the smallest to the largest. The values that divide an ordered set of elements into 100 equal parts are called percentiles. An observation at the 50th percentile would correspond to the median value in the set. Quartiles divide an ordered data set into 4 equal parts. The values dividing each part are called the first, second, and third quartiles, and they are denoted by q sub 1, q sub 2, and q sub 3 respectively. The chart displayed here shows a set of 4 numbers divided into quartiles. Notice that Q2 is the median, Q1 is the median of the values less than Q2, and Q3 is the median of the values bigger than Q2. Note the relationship between quartiles and percentiles. Q sub 1 is the 25th percentile. Q sub 2 is the 50th percentile, which is also called the median, and Q sub 3 is the 75th percentile. Standard scores are z-scores. A z-score indicates how many standard scores a value is from the mean. A standard score can be calculated from the following formula: z equals x minus mu divided by sigma, where z is the z-score, x is the value, mu and sigma are the population mean and standard deviation. A z-score less than 0 represents a value that's less than the mean. A z-score greater than 0 represents a value greater than the mean. A z-score equal to 0 represents a value that is equal to the mean. A z-score equal to 1 represents a value that is 1 standard deviation greater than the mean. A z-score equal to minus 1 represents a value that is 1 standard deviation less than the mean. Most standardized exams provide scores in terms of percentiles, which are defined as follows. The pth percentile. A value x is called the pth percentile of a data set, provided p% of the values are less than x. For example, in a recent year, the median annual salary for a physical therapist was $74,480. If the 90th percentile for the annual salary of a physical therapist was $105,900, find the percent of physical therapists whose annual salary was A, more than $74,480. Now, by definition, the median is the 50th percentile, and it tells you in the problem that the median annual salary was $74,480. So it's the 50th percentile. B, less than $105,900. Well, it tells you in the problem that the 90th percentile for the annual salary of a physical therapist was $105,900. That means that 90% of all physical therapists make less than $105,900. C, between $74,480 and $105,900. Here you really just need to subtract. Take the 50% answer and the 90% answer and subtract, and that tells you that 40% of the physical therapists make between $74,480 and $105,900. The following formula can be used to find the percentile that corresponds to a particular data value in a set of data. Here's the formula. Given a set of data and a data value x, the percentile of score x is equal to the number of data values less than x divided by the total number of data values multiplied by 100. The entire fraction multiplied by 100. For example, on an exam given to 900 students, Elaine's score of 602 was higher than 576 of the scores of other students who took the exam. What is the percentile for Elaine's score? Remember the formula. It's the number of data values less than x divided by the total number of data values. Take that fraction, multiply by 100. In this case, we're looking for data values less than 602. Read this carefully. Exam was given to 900 students, so that's the denominator of the fraction. Those are the total number of data values. But for the numerator, we need the number of data values less than 602. But the problem says that 602 was higher than 576 of the scores. If you just look at that visually, that means that the 576 scores they talk about are lower scores because the lane score of 602 was higher than those 576. So that's the number we need for the numerator, 576, and simply multiply that by 100. If you do that arithmetic, you'll find out that it comes out to be 64%. So a lane score of 602 places her at the 64th percentile. We can also use this formula to work backwards. In other words, what if we know the percentile and need to use it to find the number of scores less than that percentile? Using this example, if a student scored at the 50th percentile, how many students scored lower? Well, again, your formula, we're looking for the 50th percentile, so we plug 50 in on the left. We're looking for the number of data values less than x, we'll call that whatever variable you want to use. I chose n here. And then again, there are 900 total data values, so 900 is in the denominator. And if you write that out as an equation, you get 50 is equal to n divided by 900 in the entire fraction times 100. If you divide 100 and 900, you get a 9 in the denominator, so you really get 50 is equal to n over 9. And if you cross multiply, you'll find out that 450 students scored below the 50th percentile. Now let's talk about quartiles. The three numbers q sub 1, q sub 2, and q sub 3 that break a ranked data set into four approximately equal groups are called quartiles of the data. Quartiles meaning four, it breaks the data into four pieces. 3 slices breaks it into 4 pieces. For example, if we take this data set below and want to find the values of q sub 1, q sub 2, and q sub 3, here's how we proceed. First of all, the data needs to be ranked from smallest to largest, and this data set is ranked from smallest to largest. Once that happens, find the median. Remember, the median is q sub 2. The median, if you count the data points, there are 19 of them, so the median is the 10th one. There are 9 to the left, 9 to the right, 99 is 18. The one in the middle, the 29, is the 19th one. So the median, or q sub 2, is the middle value, and in this case it happens to be 29. Remember, if there's 2 middle values, you average them to get the median. Step 2, find the median of the numbers that are less than the median. Those are the 9 numbers to the left of q sub 2, and that value will be q sub 1. If you look to the left of q sub 2, there are 9 numbers. That means that the 5th one is in the middle. 4 to the left, 4 to the right, 4 and 4 is 8. The 9th data point is the 11, which is in the middle. That's q sub 1. Now you move over to the other side and look at the median of the values bigger than q sub 2. Those are the 9 numbers to the right. Again, there are 9 of them, so the 5th one, which is 104, is q sub 3. And that's how you break a data set into quartiles. Here's the procedure. Order the data from smallest to largest. In this case, it was already done for you, but sometimes it's not. Second step is to find the median of the entire data set. That's q sub 2. Then take the values to the left of q sub 2. The median of those values is q sub 1. Then go to the right of q sub 2 and find the median of those values, and that's q sub 3. Look at this example. The following table lists the calories per 100 milliliters of 25 popular sodas. Find the quartiles for the data. These calories are not listed in order, so this time we do have to spend some time ordering that data set. I'm not going to go through this painfully step by step, but when I did that, I counted, there were 25 data points, and when I put them in order, this is what I got. Once you've ordered, find the median. The median is q sub 2. Well, if there are 25 values, that means that the 13th one is the median, 12 on the left, 12 on the right, and the 25th one would be the 13th one. So Q sub 2 is 43. Now you move to the left and take the median of those values. Looking on the left, you can see there are 12 values. So the median is going to be, there'll be two middle values. The median is going to be between the 6th and the 7th one. So you average them. The average of the 6th and 7th, they both happen to be 39. So when you average 39 and 39, of course you get 39. That's Q sub 1. Now you move to the right and take those values. Again, there are 12 of them, so the median is going to be between 50 and 53. So if you average 50 and 53, add up 50 and 53 and get 103 and divide by 2, you'll end up with a median of 51.5. And that's Q sub 3. If the minimum and maximum values of a data set are included along with Q sub 1 and the median Q sub 2 and Q sub 3, they form what we sometimes call a 5-number summary. So just to put our thoughts together, if you take these 3 quartile values and add the smallest and largest to them, you get what I will call, and what a lot of people call, the 5-number summary. So 26 is the smallest value, 39 is the first quartile value, 43 is the second quartile value, which is the median of the whole data set, 51.5 is the third quartile value, and 73 is the largest. That's the 5-number summary. That 5-number summary is just a way of summarizing a large data set. If you have a whole bunch of data, it's really hard to think of it as meaningful because it's just so large. So if you can condense the large data set down to a smaller set of numbers, it gives you a better way of thinking about it. So if you look at those 5 numbers in the 5-number summary as being kind of a representation of a much bigger data set, that's the idea. Now you can turn that 5-number summary into something even more visual, something called a box-and-whisker plot. Has a funny name, but all you're doing is taking the 5-number summary and turning it into a picture. Let's just start back from the beginning. If you've got the data set, the median is the middle value when you've got them in order. And then you take the lower half of the data and find its median, that's Q sub 1. Then you take the upper half of the data and find its median, that's Q sub 3. And then you add on the minimum value and the maximum value. So just to summarize, going back from the very beginning, when you first start with the data set, you order the data and you come up with this 5-number summary. Let's take an example and take it all the way through the process. We'll turn it into a 5-number summary, and then we'll take that and turn it into a box-and-whisker plot. So this is an actual list of ages of presidents assuming office between 1901 and 1993. They're already in order, so you don't have to worry about that, but if they weren't, you would. There are 17 of them if you count. That means the 9th one is the median. That would be 8 to the left, 8 to the right, 8 and 8 is 16. The median value would be the 17th one. So you can see that the 1, 2, 3, 4, 5, 6, 7, 8, the 9th one, leaving 8 on the left and 8 on the right, is the median. So the median is 55. Then you take the lower half, the values to the left of the median. There are 8 of them. So there are 2 in the middle. Both are 51, so when you average 51 and 51, obviously you get 51. The upper half, the middle values are 60 and 61, and when you average those, of course, you'll get 60.5. The minimum value is thrown in, and the maximum value. So those are the 5 numbers. So the 5-number summary, minimum, first quartile value, which is the average of 51 and 51, the median, which is 55, the third quartile value, which is the average of 60 and 61, and then the maximum. Once you get the 5-number summary, we can turn it into a box-and-whisker plot. What you do is you take those 5 numbers and you make a box essentially around the middle 3. So the box or the rectangle has one endpoint at Q1, that's the 51, and the other endpoint at Q3, which in this case is 60.5, and of course the median falls somewhere in that rectangle. So do that first. Make your little box or rectangle with the left-hand part of the box being Q1, the right-hand part of the box being Q3, and it will automatically include the median. And then you put your whiskers on. The whiskers are line segments going to the left and to the right. To the left, they go all the way to the minimum value of your 5-number summary, which in this case is 42. And to the right, it goes all the way out to the maximum value in the 5-number summary, which was 69. So your box and whisker plot is simply taking your 5-number summary and doodling on it. You're essentially putting a box in the middle going from Q1 to Q3 that encapsulates the median, and then you put the whiskers out that go from the minimum value to the maximum value. So you're basically doodling on top of your 5-number summary. Now let's wrap up this section by talking about z-scores. Let's start off with an example. Consider an internet site offering movie downloads. Based on data kept by the site, an estimate of the mean time to download a certain movie is 12 minutes with a standard deviation of 4 minutes. When you download it, the download takes 20 minutes, which seems an unusually long time. On the other hand, when your friend downloads the movie, it takes only 6 minutes, and your friend is pleasantly surprised at how quickly she was able to begin watching the movie. In each case, a data value from that far from the mean is unexpected. The graph in the lower right-hand corner shows the movie download times using two different measures. At the bottom, you have the number of minutes a time is from the mean, and above that number line, you have the number of standard deviations the time is from the mean. Let's take those one at a time. First, the minutes. Remember that your time for the download was 20 minutes. Your friend's time was 6 minutes. The mean was 12, so your friend's time was actually 6 minutes below the mean time. 6 minutes minus a mean of 12 results in a difference of -6. That means that your friend's download time was 6 minutes below the mean time. Your time, on the other hand, though, was 20 minutes. That's 8 minutes above the mean time. So in terms of minutes, your friend's time for downloading the movie was 6 minutes below the mean. Your time was 8 minutes above the mean. Now let's look at the standard deviations. We're going to do a lot with these calculations later, but just quickly, if you want to look at how many standard deviations away from the mean each of those mean times is, just take each one of them and divide by the standard deviation. And remember, in this problem, the standard deviation was 4 minutes. So if you take your friend's difference from the mean, which is -6, and divide it by the standard deviation, you get a -1.5. That means your friend's download time was 1.5 standard deviations below the mean. The negative sign indicates it's below the mean. Your download time, however, was 8 minutes above the mean. Again, divided by the standard deviation of 4, that's 2 standard deviations above the mean. So your friend's download time was 1.5 standard deviations below the mean, which in raw minutes is 6 minutes below, which is the -6. Yours was 2 standard deviations above the mean. In raw minutes, that would be 8 minutes above the mean. So there are two different ways of looking at this. The number of standard deviations between a data value and the mean is known as the data value's z-score, or sometimes it's called the standard score. The z-score, or standard score, for a given data value, x, is the number of standard deviations that x is above or below the mean. Below are the formulas for those calculations, one for a population, the other for a sample. It really doesn't matter because in the context of a problem, you'll either be working with a population or a sample, but the process is the same. To get a z-score, you take the x value, subtract the mean, whether it's a population mean or a sample mean, and divide by the standard deviation, whether it's a population standard deviation or a sample standard deviation. So the process is the same. It's x minus the mean divided by the standard deviation, whether it's a population or a sample. That's how you calculate a z-score. Keep in mind, if it's a population, it's the population mean and population standard deviation, that's mu and sigma. If it's a sample, it's x bar and s, the sample mean and sample standard deviation. But the process is the same. So for our purposes, when we're working a particular problem, it's the process. It doesn't really matter whether it's a population or a sample. The information that we're given will allow us to solve the problem the same way in either case. So here, as we go back and try to summarize everything, the z-score for your download time, the z-score for the 20 minutes that it took you to download is 2. That means it was 2 standard deviations above the mean. And the z-score for your friend's download time, the z-score for 6 minutes, is negative 1.5, meaning it's 1.5 standard deviations below the mean. Let's use z-scores to examine how well a student did on his test compared to other students. You're going to practice this a lot in this section and the next one, so let's get started with this example. Raul took 2 chemistry tests. He made a 72 on the first test. The mean test score for that test was 65 with a standard deviation of 8, and he made a 60 on the second test. The mean test score for the second test was 45 with a standard deviation of 12. In comparison to the other students, did Raul do better on the first test or the second test? This is a perfect place to use z-scores. We're going to calculate the z-score for each of Raul's 2 tests and use that as a measure of how he did relative to the rest of the class. Remember, the z-score, whether it's taken from population or a sample, basically you take the x value, subtract the mean, divide by the standard deviation, whether it's population or sample. So let's look at each test. For Raul's test 1, he made a 72 on the first test. So the z-score for that 72, you take the value, the 72, subtract the mean, which was 65, and divide by the standard deviation, which was 8. The 72 is the value, which is the score on test 1. 65 is the mean, 8 is the standard deviation. The value minus the mean divided by the standard deviation. If you simplify that, you'll get 0.875. Now let's do the same thing for test 2. For test 2, that's the z-score for a score of 60 on the second test. You take the value, which was the test 2 score, 60, subtract the mean on that test was 45, and divide by its standard deviation of 12. Take the value, subtract the mean, divide by the standard deviation. If you do that calculation, you get 1.25. So looking at those 2 z-values, you can easily see that Raul had 0.875 standard deviations above the mean for his test 1 score and 1.25 standard deviations above the mean on test 2. So he outperformed the students on test 2 more than he outperformed the students on test 1. So in comparison to the other students, Raul's score was better on test 2 than on test 1. Now that's in comparison to the other students, not as a raw score. We can also work backwards on these problems and find a value that produces a certain z-score. For example, suppose a blood pressure test was given to 450 men. The results gave a mean systolic blood pressure of 119.7 with a standard deviation of 13.9. If the z-score for one of the men was 2.19, what was his systolic blood pressure reading? And round your answer to 1 decimal place. Notice, as I said earlier, we're working backwards because this time we know the z-score. In the previous problem, we were computing the z-score. So what we have to do is write down the formula for calculating a z-score. Again, it doesn't really matter if it's a population or a sample. And we're solving for x this time, but we know that the z-score was 2.19. We know the mean blood pressure was 119.7, and we know that the standard deviation is 13.9. So you plug those numbers into the formula, and I chose the population one, but if you'd chosen the other one, the process is the same. It's just whether you're dealing with a sample or a population, and it really doesn't matter in this problem in terms of the calculation which one you choose, because the process is the same. So you put 2.19 in for z. You're solving for x, remember, so you leave the x in there. The mean was 119.7, so that goes in for mu, and the standard deviation was 13.9, so that goes in for sigma. And now, if you cross multiply, think of 2.19 as 2.19 over 1 and cross multiply, or think of it as multiplying both sides by 13.9. In either case, you'll end up with 30.441 is equal to x minus 119.7. And if you add 119.7 to both sides, you'll find out that x is equal to 150.1. So the systolic blood pressure reading of a man whose z-score was 2.19 must have been 150.1. Here I've pulled out some material from the sections on how to read a standard normal table, and I want to treat that sort of as a topic on its own because it's a tool that we use to answer questions that we're interested in knowing the answers to. So it's really important to be able to use that tool easily and without struggling, so that when you get to the problems where you need it, you'll have it. So I want to extract the part of the material related to learning how to read that table and do it here sort of as a separate standalone topic. And I want to do that by just sort of explaining a little bit about where we stand and what the importance of this is. In situations involving some statistical problems, tables are quite often used to determine areas under sections of a curve, and these table values actually represent probabilities. So the ultimate reason we're looking for these areas that are tabled is because they're probabilities that we're interested in. In the following section, 13.4, we will lean heavily on what's called a standard normal table, and I could wait and talk about that as a part of the topic in 13.4, but because it'll help me balance the lecture times, I'm actually going to take this material out and just talk about it as a standalone topic, and then when we get back to section 13.4, I'll fill in more details about how this standard normal table helps us to solve the problems in that section. But for now, we're more learning how to do something and let the why come later. Below, I just want to say a couple of things, 2 or 3 things about the relationship between z-scores and the standard normal table for now. Let the rest of it come later. First of all, just remind you, we learned how to convert data values to z-scores. We've already done that. This so-called normal distribution of z-scores is what we call the standard normal distribution, and that standard normal distribution has a mean of 0 and a standard deviation of 1, always. But probably the most important point, one of the most important points here, is that the total area under the standard normal curve is always equal to 1. If you look at this curve, the total area underneath it is 1, and you'll also notice that it's symmetric. If you took a knife and just cut that curve right down the vertical line at 0, you would have 2 symmetrical pieces. That has an implication about area. If you cut that curve so that you only have half of it, if the total area under the curve is 1 and those 2 pieces are symmetric, that means each piece has an area of a half. So the right part has an area of 0.5 or half. The left part has an area of 0.5, and of course 0.5 plus 0.5 is 1. The total area under the curve is 1. So the idea of the symmetry of the curve and the idea that the total area under the curve is 1, and that you can cut that curve essentially into 2 symmetrical pieces whose area each has 1/2 is important. Now let's take that and use it to work problems where we have to know how to read this standard normal table. For example, this is what you will see if you have look in the appendix of the book, or if you look online in your software and pull it up. This is the standard normal table you'll get. you've got to keep in mind that this table gives you certain values that have a graphical meaning, and I put that up on the left of the table. Those areas, which is what that table shows, represent the area under the standard normal curve from 0 to the right to some particular value of z. So for any particular value of z, you can look up in that table what the area would be. So as a simple example, what if I told you to find the area under the standard normal curve from z equals 0 to 1.44? Well, that graph on the left looks of the same form as the one on the right, which means you can read that value right out of the table. All you have to do is let z be 1.44, go to the table and find it. I'll blow it up so you can see it better, and you can see that the area corresponding to a z value of 1.44 is 0.425. So you take that number, and that represents the area under the standard normal curve from 0 to 1.44. Simple. Very simple when the left boundary of the area starts at 0 and the z value is to the right. In other words, positive. That's the simplest possible case. But we can also deal with it if z is negative by using the symmetry of the graph. If I start at 0, but I want to know the area from minus 0.144 to 0, so that the 0 boundary now is on the right, the symmetry of the graph tells me that it's the same as the area going from 0 to 1.44. That means I can still look up the 1.44 in the table and still apply it, even though it's going in the negative direction. The area of both of those pieces is the same because of the symmetry of the graph. To sort of summarize that situation, anytime you're looking for an area under the standard normal curve where one of the boundaries is 0, all you have to do is look at the z value without paying any attention to the sign, whether it's positive or negative. Look that value up in the table, and that will be the area you're looking for. Simplest possible case. What if that's not the case? What if you're looking for something? Those are called the tails of a distribution. When you go to the far right or to the far left, those are called the tails of the distribution. What if you want to find the area of one of those tails? For instance, what about the one to the right? You want to find the area under the standard normal curve for z greater than 1.44. If you understand what the values in that table give you, this is pretty simple. And also the symmetry stuff. The fact that if you cut the curve in half at z equals 0, you get half the area to the right. So if you think about those two things together, the number 1.44 is still important. That gives you 0.425, but remember what that gives you. That gives you the area between 0 and the z value 1.44. So it gives you that. But you're not looking for that. You're looking for the shaded area to the right. Here's where the symmetry comes in. We learned that the graph is symmetric, so half the area is to the right of 0. So all you need to do is take that 0.425, subtract it from 1/2, and whatever's left is the area to the right. Easy enough. The area is 1/2 from 0 all the way to the right. You accounted for 0.425 of it between 0 and z, so the rest of it, which you get by subtraction, is the area that you're looking for. The other variation of that is if you were looking for the left tail instead of the right tail. It would be the same, right? Because of symmetry. So again, the fact that z is equal to negative 1.44 going to the left doesn't change the fact that the area is still 0.075. So again, for the tails, you can ignore the sign, plus or minus, just look up the 1.44, doesn't matter, and subtract it from 0.5, and that'll give you the area to the right of 1.44 or the area to the left of negative 1.44. The sign actually doesn't matter because the table only gives you positive z values, and because of the symmetry, you can figure it out either way. Do another one. What if I wanted to know this area? I wanted to know the area between z equal negative 1.25 and z equal 1. Now this time, the area includes, it crosses over z equals 0. Whenever that happens, what you need to do is break it into two areas and treat it as if it were two different area calculations, and then add the results at the end. So you just look them up. Think of one area as being the part to the right of 0, and think of the other area as being the part to the left of 0, and work them as two separate area problems, and then sum the results. So let's just start with the one on the right first. That's a standard problem where you just need to look the z value up in the table. So you go to the table, look for z equal 1, and you find out it's 0.341. That's the area to the right of 0. Now take the area on the other side. It's negative 1.25, but remember, because of the symmetry, the area is the same as it would be if you went to the right to positive 1.25. So you still just need to look up 1.25 in the table. And that comes out to be 0.394. So you have both of those areas. If you want the total area, you just add them up. 0.394 plus 0.341 is 0.735. So the area under the standard normal curve between z equal minus 1.25 and z equal 1 is 0.735 square units. You see how this works? It's almost like playing a game. You've got to figure out how to handle those areas in different situations. How about this one? We want to find the area to the nearest thousandths between z equal 1.24 and z equal 1.81. If you sketch it out, you'll see that it's the area that doesn't touch z equals 0. This is the first one that didn't either include or touch z equals 0. So you're looking for that area there. Well, how would you do that? Think about it. What is the area associated with z equal 1.81? If you were to look at it in the table, you'd get 0.465. What does that represent? That represents the area from 1.81 back to 0. Well, that's more than the area you want. You've got too much. You need to take some away. Well, how much do you need to take away? Well, you need to take away the part that goes from 0 to 1.24. So, the light bulb should come on. All I have to do is take that 0.465 and put it aside and go back to the table and look up 1.24, and that gives me 0.393. That gives me the area that I want to get rid of. If I take the 0.465 area and subtract off the 0.393 area, I'm left with the area that I want, which it turns out to be 0.072. So there's a little trick. Whenever the area doesn't include or touch z equals 0, you have to take the largest z value, look up the area, the smaller z value, look up the area, and then subtract the two. So the area under the standard normal curve between z equal 1.24 and z equal 1.81 is about 0.072 square units. Do another one. This time we're looking for the area between z equal negative 2.24 and negative 1.61. So this time both borders are to the left of 0. So we're looking for that area between. But because of symmetry, the area over to the left can be thought of as being the same as the area to the right. So instead of looking for the area between negative 2.24 and negative 1.61, just look for the area between 1.61 and 2.24. And the areas will be the same. And you can see by the symmetry that that's got to be true. And we just talked about how to do that. You take the larger z value, look up the area, take the smaller z value, look up the area, and then subtract. So the larger is 2.24. Look it up in the table, and you'll get about 0.487. That's the area from 2.24 all the way back to 0. Then look up the smaller z value, 1.61. That turns out to be 0.446. That's the area you want to get rid of. So if you take that away from the larger area, you'll end up with an area of 0.041. So the area under the standard normal curve between z equal negative 2.24 and z equal negative 1.61 is about 0.041 square units. You sort of see the game you're playing now. It's almost like playing a game. And to wrap it up, let me just summarize what I've talked about and sort of emphasize how it works. The simplest case is when one of the values happens to be z equals 0. Either 0 going to the right, or you've got a negative z, which means you're coming from the left towards 0. But in one case or the other, one of the boundaries is z equals 0. That's the simplest case. And in that case, whether the z value is positive or whether the z value is negative, you simply ignore the sign, look up the positive value of z, and that will be the answer. Second case, what if both values are positive or both are negative? That would be the case. The first one is where both z values are positive. The second one is both are negative. And we talked about that. All you have to do is take the positive values, whether they're negative or not, just take the positive values, look up the bigger positive number, the smaller positive number, and subtract. Larger minus smaller, and the difference is the area you're looking for. Third case, one value is positive and one is negative. Whenever one value is negative, one's positive, that means z equals 0 is inside. And when that happens, you break the graph into two pieces. You treat each piece as a separate problem and add the results. And we did one of those, at least one of those. And the last case is the area where you're doing the tails. Either z is bigger than some number or z is smaller than some number, where the value of a would be positive in the first case or negative in the second case. For example, either tail. The first one has the right tail where you have z greater than some positive value, or the left tail where z is smaller than some negative value. The procedure there, that's where the 0.5 came in. Remember the symmetry? You can look up the z value, ignoring the sign, and subtract it from 0.5. If you understand that, it's going to make your work in section 13.4 so much easier. So you might want to go back through this again and make sure you understand every bit of it. It's very important, and it'll make your life a lot easier in section 13.4.